In physics, we observe the real world in order to develop trends and understandings of how and why objects move. We observe so we can apply this information. One of the most unique places is in the world of animation. Pixar animators need to create realistic and believable environments, so they use real physics. In the movie Up, Carl Fredricksen uses his extensive helium tank collection and knowledge of physics to effectively destroy the property value of his home by moving it to South America via balloon.
House.
Because the balloon house is moving at a constant velocity, or is floating still, we can assume we have balanced forces. The house has a mass of 156,489 kilograms. Assuming all of the balloons together count as one tension force, try drawing a fully labeled force diagram of the house as it floats without moving, so it's stopped, which is a balanced forces. In order to do this, we need to start with our object, usually a dot. In this case, we'll use a house. The force of gravity always points straight down. We're looking at the balloons as the strings that's holding the house up. So we're looking at a tension force in this case. So that's going straight up. These forces are equal. They're balanced out. In order to find the gravitational force, as long as I know the mass, I know the gravitational force. I take the mass, which is 156,489 kilograms, times the gravitational force constant, 9.8. When I multiply those together, I get 1,533,592.2 newtons. That's our gravitational force. This is a balanced force example. So the downward force balances the upward force. Fg equals Ft. So if the downward force, the gravitational force, is 1,533,592.2 newtons, the same can be said for the tension force. Now, instead of finding the force of all the strings together, if we wanted to know the divided force amongst each string, we'd have to look at how many balloons there are. There's 750,000 balloons individually tied off. What is the tension force in each balloon string? As a little hint, how many equal up forces are balancing the down force? In order to do this problem, you would divide the total upward force by how many individual forces it's being split out to. So in this case, how many individual strings are being tied off. So I would take 1,533,592.2 newtons and divide it by 750,000. That's going to give me an individual force for each string, a tension force, of 2.04 newtons. In the movie, Mr. Fredricksen's house doesn't just fly up, it can fly forward as well. So we are seeing vertical and horizontal forces at work. As the house flies forward, the sails pull the strings, creating an angle. The house still has a mass of 156,489 kilograms. When it flies, an angle of 45 degrees is created in the string. If the house is flying at a constant velocity, what's the tension force? So because it's going at a constant velocity, we know that it's balanced forces. Let's start with our force diagram. Gravity is always a great place to start because every force diagram will always have gravity going straight down. We already calculated the force of gravity for this particular house in our last problem. We're going to label the force of the wind on the sails as an applied force because it's the force that's pushing the house forward. Because it is wind, that means it's air resistance, and you could argue that this is a friction force as well. The tension force is now pulled at an angle as the balloons drag behind. Every time you have an angled force, you always need to have a horizontal and vertical force to complete the triangle. So this is at a 45-degree angle. I'm going to complete it with Ftx and Fty. my x and y components for this tension force. At this point, we've entered all of the given information. We need to start making some inferences. I know that this is a balanced force because it's a constant velocity. It's not accelerating up, it's not accelerating down, it's not accelerating left, it's not accelerating right. So we can assume that the forces to the left are equal to the forces to the right. The forces going up are equal to the forces going down. Write out your force equations. Fg equals Fty. Because Fg goes down, it's going to balance up. Fa equals Ftx. Ftx balances Fa. They are opposing forces. Since there's only one force going down and one force going up, if Fg is 1,533,592.2 newtons, so is the y component of the tension force. Whenever we have angled forces, that means we have right triangles, which means trigonometry is not far behind. If we look at the triangle, we currently have a reference angle of 45 degrees. We're looking for the tension force, which is our hypotenuse, the red force. And then we are given, or at least we derived, that the tension force, y component, is 1,533,592.2 newtons. That's the opposite side. It's opposite from 45 degrees. So if we use SOHCAHTOA, we have opposite. We're looking for hypotenuse. That's so. So we're going to set up our sine equation. The sine of the given angle equals opposite over hypotenuse. Well, right now the opposite is Fty, 1,533,592.2. We don't know the hypotenuse. That's the tension force that we're looking for. So we'll just put a variable in. Whenever there's a variable down below, we're going to switch out the sine of 45 and that variable. When we flip those out, we end up with x equals 1,533,592.2 divided by the sine of 45. Little plug and chug in our calculator, and there is our answer. 2,168,826.89 newtons. That is the tension force being pulled on the string as the house flies forward.
What was that, Mr. Fredrickson?
We can't be close to the ground yet.
Russell and Mr. Fredrickson have a combined mass of 91 kilograms. They're completely stopped, and the hose is at an angle of 35 degrees. Russell drags his feet with a frictional force of 475 newtons. What is their normal force? Now, they're stopped, which means we have 100% balanced forces. They're not moving forward or backwards. That means they can't be accelerating forwards or backwards. They're not moving up or down, so that means they can't be accelerating up or down. All balanced forces. As always, we start with a well-labeled force diagram. This time around, we're not looking at the house, we're looking at Russell and Mr. Fredrickson and the forces that are being acted on them. So we start with our object. Gravity is always there. We need to calculate the gravitational force. We do this by simply taking their mass, 91, times 9.8 to get 891.8. There's a frictional force that they gave us, 475 newtons. This is coming from the force of Russell's feet rubbing against the ground, creating heat. Since they're standing on a dangerous but still solid surface, they're going to have a normal force. That cliff is pushing up on them. They take one step forward, that normal force will no longer be there. The house is pulling up on them using the garden hose at a degree of 35. The house is creating a tension force with the garden hose at an angle of 35 degrees. Whenever we have an angled force, we need to make sure that there's an x and y component to make a right triangle. Once all of the information that's been given to you has been applied to the force diagram, you need to start making inferences. I see 2 up forces, 1 down. I see 1 left, 1 right. Well, I know my force pulling to the right, so my force pulling to the left is going to be the same, 475 newtons. When we balance the up forces and the down forces, we need to remember that there's 2 forces being pulled up, and we can't assume that they're equal, unlike the balloon problem earlier. So we need to set up a force equation. The gravitational force, which is our down force, is equal to the sum of the normal force and the y, or vertical component, of the tension force. Once we have this general formula, we can plug in the information that we know from our force diagram. Well, I know that the gravitational force equals 891.8 newtons. I don't know Fty and I don't know Fn. However, because Fty is part of a triangle that has at least one given side and at least one given angle, we can find any of those other sides. Using 35 degrees as our reference angle, we're looking for Fty, which is the opposite from that angle. Ftx is given, or at least we were able to derive, 475 newtons. That's our adjacent side. We have opposite that we're looking for, adjacent that we already have given to us. That's TOA. So we're going to set up a tangent equation. So the tangent of the given angle of 35 degrees equals opposite over adjacent. The opposite side is Fty. It's unknown, so I'm going to put in a variable. The adjacent side is Ftx, 475 newtons. I can plug that in. If the variable is on the top end of that ratio, then we're going to multiply both sides by the denominator. It's really a one-step equation. What's happening to the variable x? We're dividing, so we need to multiply by 475 on both sides. 475 times the tangent of 35, quick calculator check later, we end up with 332.6 newtons. Now you need to be very careful at this point, because the question is, what is their normal force, not what is the y component of the tension force. Just because you've completed a calculation doesn't mean the problem's over yet. Now we have 2 out of the 3 magnitudes for the 3 forces in our force equation. We have 891.8 for the gravitational force, and the y component of the tension force is 332.6. Now it's just a simple one-step equation. We're going to solve for the normal force, get it by itself. Our final answer, 559.2 newtons. That's how much is being pushed up on them. It's important to note that not all normal forces are equal to their opposing gravitational force. In this case, 559.2 is less than 891.8 because the house is pulling up on them. It's alleviating some of that force. That's what angled forces do.